axis, and the point of intersection of the x and the y will be known as the origin. So along the x, to your right, we shall have the positive x-axis, and then to the left of the origin, we shall have the negative. And then above the origin, we shall have the positive y, and then below the origin, we shall have the negative y. So whenever we are measuring angles, we always prefer to start from the positive x as our reference point. So between the positive x and the positive y, this will be known as quadrant number 1. Between the positive y and the negative x, this is quadrant number 2. Then between the negative x and the negative y will be known as quadrant number 3, and this will be known as quadrant number 4. So since this is our reference point, it will be 0 degrees. Then we shall have a 90 degrees. We shall have 180. We have 270. And then we shall have 360 degrees to form a full revolution, because we measure angles that are positive from the positive x in the anti-clockwise direction. So those are positive angles. And then if we have to measure the angles in the clockwise direction, we shall be measuring the negative angles. All right. So if I create a point, maybe a point P within the first quadrant, and then I form a distance OP, I can draw a triangle which is right angled by dropping that. So the horizontal distance will be x, and then my vertical distance will be y, and then I can let my OP be r. But we know that from any right angled triangle, for as long as that's a 90 degree, the side that is opposite the 90 degree will be always known as the hypotenuse. And then the side that is adjacent to the angle will always be known as the adjacent next to the angle. And then the side that is far away, that is opposite, will be known as the opposite side of the triangle. From our trig ratios, we know that the sine of an angle is the opposite over the hypotenuse. And then the cos of an angle will be the adjacent over the hypotenuse. And then the tan of an angle will be the opposite over the adjacent. So some learners normally use the acronym SOHCAHTOA, just for remembrance. So the S stands for the sine, opposite over hypotenuse. And then we have the cos, adjacent over hypotenuse, and then T is for the tan, which is opposite over adjacent. So if I'm to focus on quadrant number 1, what happens in quadrant number 1? I'm going to compare these trig ratios, and I identify the signs that they take in each of the quadrants before we can get to the reduction. So in quadrant number 1, if the angle formed by the line OP is theta, so the sine of theta in this case is going to be my opposite, which is y, and then my hypotenuse is r, and then the cos of theta will be the adjacent, which is x, over r, and then the tan of theta will be the opposite, which is y, over the adjacent, which is x. So what I can notice is that since in quadrant 1, the horizontal is positive and then the vertical is also positive, all these trig ratios are going to end up being positive. Then when I move to quadrant number 2, so in quadrant number 2, I could draw an extension in that format, and then that is our 90. So the horizontal distance is going to be negative x, and then our vertical distance is going to be a positive y. So the angle will be measured in a way that we still refer with a positive x. So this angle of ours will be known as the theta. And let's say that will also be known as the theta, as we shall explain later on. So in as much as it's from the positive x to this, it can be reduced to something like that. So that's our r as well. So in quadrant number 2, the sine of theta is going to be the opposite, which is y over r. If I'm talking about the cos of theta, it will be the adjacent. Now my adjacent is a negative x over the hypotenuse, which is r, and then the tan of theta will be the opposite of adjacent, so it's y over negative x. So what I can see is that in the second quadrant, the sine is positive, the cos is negative, and the tan is negative. So in quadrant number 2, it's only the sine that will be positive. The rest of the trig ratios will be negative. Then I'll look at quadrant number 3. If I'm to draw an extension and then another triangle there, so the horizontal is still negative x, and then the vertical is negative y. That can still be our r. Just a humble reminder that the hypotenuse will never be negative in nature. So the sine of theta will be the opposite over the hypotenuse, which is negative y over r. The cos of theta will be the adjacent, which is negative x over r. And then the tan of that theta of ours now is going to be the opposite, which is negative y over negative x. So remember, the theta is still from the positive x up to this line of ours, which can still be reduced to just that internal angle between the x-axis and then that line. So from the observation, we can see that here, if we reduce everything, the sine is going to be negative, the cos is going to end up being negative, and then negative divided by negative, we end up with a positive. So in quadrant number 3, it's only the tan that is positive. The rest of the values will be negative. Then I move on to quadrant number 4. So in quadrant number 4, what I know is that if I do my extension again, create the triangle, the horizontal distance is going to be x, the vertical will be a negative y, and then that is r. So while measuring the angles, we shall still have the same measurement from the positive x up to that. That's the theta, which is the same as that theta inside. So in quadrant number 4, the sine of theta will be the opposite, which is going to be negative y over the hypotenuse, which is r. Then the cos of theta will be the adjacent, which is the positive x over our hypotenuse, which is r. And then the tan of theta in that case is going to be the opposite over the adjacent, which is negative y over positive x. So from our overall simplification, the sine is going to end up being a negative, the cos is going to end up being a positive, and then the tan is going to end up being a negative. Now, if I'm to draw a proper cast diagram, a fresh one, it's going to look like that. And extend that. So we said this is 0, 90, 180, 270, as well as 360 degrees. So we said in this case, quadrant number 1, all the trig ratios are positive. In the second quadrant, it's only the sine that is positive. In this quadrant, it's only the tan. And then in the last quadrant, it's only the cos that is positive. That's why this thing is named cast, because of the letters. Okay. Now, we shall go deeper with this. So this quadrant number 1, since we know that the angles are between 0 and 90, there is another notation of representing angles, whereby we focus on the 360, and then we also focus on the 180. And so this quadrant number 1 will be labeled as the quadrant of 360, plus an acute angle theta. Quadrant number 2, since the quadrant is less than 180, we shall denote it as 180 minus theta. And then quadrant number 3, since it's after 180, it will also be known as a quadrant of 180 plus theta. And then in the fourth quadrant, that is less than 360, we can denote it as 360 minus theta. Now, if we have a scenario whereby we're looking at quadrant number 1, and in quadrant number 1, they're asking us to reduce the sine of 360 plus theta. We say this can be reduced to a positive sine theta because in the first quadrant, the sine or the trig ratios are all positive. Then the cos of 360 plus theta, since it's in quadrant number 1, the cos will be positive also. And then if we have the tan of 360 plus theta, this can reduce to a tan of theta, or the trig ratios being positive. That is quadrant number 1. And then in quadrant number 2, which is 180 minus theta. So if we have a scenario of sine of 180 minus theta, we say it's only sine that is positive. So this will reduce to a positive sine of theta. So if we get the cos of an angle, let's say 180 minus theta, we shall always end up with something as negative cos. And then if we have the tan of 180 minus theta, this will reduce to a negative tan of theta. And then in quadrant number 3, we said it will only be tan that is positive. So we shall have a scenario of 180 plus theta. This will reduce to a negative sine theta. And then if we have cos of 180 plus theta, this will be a negative cos theta. And then if we have 180 plus theta, it will end up giving us a positive tan theta. And then in quadrant number 4 is the cos that is positive. So that's going to be sine of 360 minus theta. This is going to be negative sine theta. And then the cos of 360 minus theta will give us a positive cos theta. And then if we have the tan of 360 minus theta, this will reduce to a negative tan of theta. Now, we need to know this by heart, and we just need to remember what is happening with the reductions. For as long as you can memorize the cast diagram, then the rest will be easy to follow through. Then besides this, we also use the complementary angles. So we know that complementary angles will be basically a combination of angles that give us 90 degrees. So two angles, let's say theta plus alpha, must give us 90 degrees. These are complementary angles. So if we associate the complementary angles with the trig ratios, if we have, let's say, the sine of 90 plus or minus theta, this must reduce to a cos of theta. And then if we have the cos of 90 plus theta, since we have a positive, we shall end up having a negative sine theta from the compound angles. We can always get that. And then if we have the cos of 90 minus theta, this will give us a positive sine of theta. And then lastly, under this, what if we're dealing with the negative angles? Negative angles. So if we have, let's say, the sine of a negative angle, this will be the same as negative sine of that angle. Then if we have the cos of a negative angle, this will always be ignored because we shall always end up with the same value as the cos of a positive angle. And then if we have the tan of a negative angle, take the negative out, and then you express it just like that. And then we also have some identities that we need to remember. identities like the sine of an angle over the cos of an angle will always give us the tan of an angle. And then if we have the cos squared of an angle plus the sine squared of an angle, we always end up with a 1. And then if we have, let's say, sine 2 or sine twice of an angle, this can be reduced to 2 sine of the angle times the cos of the angle. And then we also need to remember the double angles of cos, whereby cos 2 theta, this can be expressed first of all as cos squared theta minus sine squared theta. Then when you go further, it can still be expressed as 1 minus 2 sine squared theta. That is when you convert the sine, the cos theta, into an element of sine. And then we're saying this can also be expressed as 2 cos squared theta minus 1. That is if we change this sine squared into a cos just from this formula. Because we know that from here, the cos squared theta is going to be 1 minus sine squared theta. And then if we want the sine squared theta to be the same as 1 minus cos squared theta. All right, so let's try to look at some questions. So question number 1, they are telling us to simplify the following expression into a single trigonometric function. So with this question, it could be a combination of reduction, identities, factorization, and a whole lot of things. So what we need to know, we have 180 plus x, we have a 90 plus x, and then we have cos 4x, and then sine to the 4 of x. So what we shall do, in this case, we shall reduce the top part using the reduction formulas. And then since there's a 1, there's a 1, there's a minus, this looks like a difference of 2 squares that we need to apply by the denominators. So this is going to be 2, the sine of 180 plus x. I'm multiplying it by the sine of 90 plus x, and then over the cos of 4 to the x minus the sine of x to the 4. So from the first part, since 180 plus x is quadrant number 3, and in that quadrant we know that it's only the term that is positive, so sine will be negative. So I'll reduce that to a negative sine x. Since there is a 2, so the 2 assumes negative sign. And then these are complementary angles. We said the sine of 90 plus must always reduce to the cos. Then over, I'll find the difference of 2 squares here. So I'll have cos squared x minus sine squared x. That's my first bracket. And then my second bracket will be cos squared x plus the sine squared x. Then what I know is that from my identities, the cos squared x and the sine squared x will give me a 1. And I know that 2 sine x cos x will reduce to sine 2x. So I'll come down and say I have a negative 2, sorry, negative, and then I'll combine this entire thing to give me negative sine 2x. And then cos squared minus sine squared, that's a double angle of cos, so that is cos 2x. But we know that sine of an angle divided by cos of the same angle will give us a tan. So this will reduce to negative tan 2x. So that is the single trig ratio that we have. Then question 1.1.2. They're asking us for which values of x between 0 and 360. For x is a set of 0 to 360, is the expression undefined. For which values do we find the expression undefined? So in normal algebra, we know that an expression will be undefined for as long as the denominator is 0. So from this whole expression, our denominator is cos 2x. So if I have the cos of 2x being equated to a 0, what will be the values of x under this scenario? So then I'll find 2x and the arc cos of 0. So my 2x will first of all give me a 90. And then when I solve for x, I divide both sides by 2. So my x is going to end up being a 45. So x is a 45. And then the other angle will be 270 degrees, where the cos of an angle is 0. So then I divide both sides by 2. My x becomes 135 degrees. So those are the two angles between 0 and 360 that we shall have that. So those are the two solutions. And then question number 1.3. 1.3, they want us to prove that the cos of 3x over cos x is equal to that. I'll just jot it this side. So we're saying the cos of 3x so the question is saying the cos of 3x over the cos of x is the same as 2 cos x minus 1. 2 cos x minus 1. The cos of 3x over cos x is equal to 2 cos 2x. Sorry. 2 cos 2x minus 1. So whenever we have proof questions, it's always advisable to start from a side that is having more items. So when you look at the left hand side, we have the cos 3x and then we have the cos x. And then on the right hand side, we only have 2 cos 2x minus 1. So I will choose to start from the left hand side so that I move towards obtaining the right hand side. So when I'm proving, I do not have to include the right hand side within my proof. That should be my last statement. So cos 3x can be written as the cos of x plus 2x. And then this is over the cos of x. So from the compound angles, I'll expand that. And then I'll have the cos of x. And then cos 2x minus sine of x. And then the sine of 2x divided by the cos of x. Then I can change the sine of 2x into 2x cos x. So this is going to be cos x times the cos 2x minus the sine x times 2 sine x cos x. Everything is over cos x. So from the numerators, I can see that there is a cos x here and then there is a cos x there. I can factorize that out. So then I'm going to have cos x outside. I'll be left with the cos 2x minus 2 sine squared x. I'll divide this by the cos x. So this cos x will cancel that cos x. And then I'm left with cos 2x. So I need to change the sine squared x into an element of cos. as a function, of course. So that's going to be minus 2 into 1 minus cos squared x. Then when I open this up, I'll have cos 2x minus 2 plus 2 cos squared x. So I have the cos 2x here, but this is cos squared x. But from the different representations of the double angle of cos, we said we have a number of ways of expressing it. So what I need to do, I'll break down this negative 2 so that it's cos 2x minus 1 and minus 1. And then I'll add the cos squared x. So that when I combine one of the negative ones and the 2 cos squared, I'll end up with a cos 2x. So that will be cos 2x minus 1 plus a cos 2x. So then this cos 2x plus the cos 2x gives me 2 cos 2x minus 1. And this is equal to the right hand side. So that's where the proof will stop. Then I'll look at question number 2. So in question number 2, I'm being told that the sine of 31 is equal to p. So they want us to determine the following without using a calculator in terms of p. I know many times learners will rush with the calculator and then they punch in the sine of 31. And then they end up with 0.5150 something. So in that case, you'll not be able to obtain what is needed because the question is specific without using a calculator. Then when they say we want the answer in terms of p, which means the answer that we get must have a component of p with it. So regardless of which angle you've been given, try as much as you can to express it at least in terms of the given angle, let's say 31. Or if it's not a 31, then it should be a multiple of 31, so that we always go back to the p's. Now, some of these questions might need the use of sketches where you draw a triangle and then use that. But in this case, I'm going to try to avoid that. So if we have the sine of 149, the first question I'll ask myself, where do I find 149 on a Cartesian plane? So 149 is in quadrant number 2. But I know that in quadrant number 2, the format will be 180 minus an angle. So it's upon me to choose which angle do I subtract from 180 to give me 149. So that will be the same as 180 minus 31. So when I have 180 minus 31, it's the same as the 149. So I've expressed this 149 in relation to my given angle. So when I reduce this, I know that the sine is positive in quadrant number 2. So this is going to reduce to the sine of 31. But I know that the sine of 31 is the same as p. So that becomes my 2.1.1. And then 2.1.2, I have the cos of negative 59. So from our negative angles, we say the cos of a negative angle will be the same as the cos of a positive angle. Now, since this 59 is less than 90 degrees, I can choose to use the complementary angles, since I don't see any way in which the 59 can be closely linked to the 31 directly. So if I try to use the complementary angles, I'll say cos of 90 minus a certain angle, which is 31, I'll end up with a 59. So this 59, I've expressed it in that format. But I know that with the complementary angles, if it's a cos of 90 minus, I must end up with a positive sine of 31. And from the question, they told me sine of 31 is p. So which means my answer here again is a p. And then 2.1.3. We have the cos of 62. So when I look at 62, yes, I know it's an acute angle, it's less than 90. But this 62 is twice the 31. So what I can do, I can say cos of 2 times 31, which is going to give me a double angle, of course. Since I don't want to use a sketch and I want to stick to the sine, so I can use a format of double angle, of course, that is having sine. So that's going to be 1 minus 2 sine squared of 31, which is 1 minus 2. I know that the sine of 31 is p, so that will be p squared. And then that becomes my final answer. Then question 2.2. They want us to simplify this expression into a single trig ratio. So we have the tan of 180 minus theta. We're multiplying it by the sine squared of 90 plus theta plus the cos of theta minus 180 times the sine of theta. So we have reductions involved. So 180 minus will be in quadrant number 2. 90 plus will be for complementary angles. Then we have a scenario here. 180 minus, theta minus 180. From the notation we've been using, we have been having the 180 minus 180 plus, 360 plus, 360 minus, 90 plus, 90 minus. So in this case, where the angle comes before the 180 or the 360, it's advisable that you factorize out the negative sign so that this can become the cos of negative now 180 minus theta. So this is what I'm gonna use. So 180 minus is in quadrant number 2. So the tan is negative in that quadrant. And then 90 plus, we say that will give us, for as long as sine, that will give us a cos squared of theta. And then we are adding. We say the cos of a negative angle will be the same as the cos of a positive angle. But since this is 180 minus, which is quadrant number 2, cos is negative. So that will give us a negative cos. So step number 1, start by ignoring this negative sign, since the cos of a negative angle will be the same as the cos of a positive angle. Then if I'm left with just cos of 180 minus, then when I reduce this from quadrant number 2, I'll end up with a negative cos. Then I'll multiply this with a positive sign. Then I can break down the tan theta to negative sine theta over the cos of theta times the cos squared of theta. A positive and a negative will give me a negative. I have cos theta times the sine of theta. So we know that cos squared theta is the same as cos theta times cos theta. So negative sine theta over cos theta times cos theta times another cos theta minus cos theta times the sine of theta. So one cos cancels one cos. So I'm just going to be left with negative sine theta, cos theta minus cos theta, and then sine theta. So this gives me negative 2 sine of theta, cos of theta, which will just reduce to negative sine 2 theta. And that becomes our solution. That becomes our solution. Then question 2.3. 2.3. So in 2.3, they want us to prove an identity. Which identity is sine 2x plus sine x is equal to that. Just get rid of this. Okay, so we're saying if we have the sine of 2x plus the cos of 2x, sine of 2x plus the sine of x, we're dividing it by the cos of 2x plus the cos of x plus 1. This must give us the tan of x. Now, we have more terms on the left-hand side compared to the right-hand side. And remember, the right-hand side is only having a tan. From our identities, we say tan can be expressed as sine over the cos. So since on the top I'm only having the sine ratios and then bottom I'm having mostly the cos, I'll start by breaking down this sine 2x so that it is 2 sine x cos x plus my sine x. I say left hand side, and then I'll divide this. I can break down this cos 2x. I would prefer to have everything in terms of cos at the denominator. So this will be 2 cos squared x minus 1 plus the cos x and then plus 1. Then from the numerator, I can see that the sine is common, so I can choose to factorize that. So I'll have my sine x outside, and then I'll be left with 2 cos x plus 1, and then over. So since this is a negative 1 and this is a positive 1, those ones will cancel out, and I'll be left with just 2 cos squared x and then a cos x. So still cos is common. So that is cos x outside, and then I'll have 2 cos x plus 1. So the brackets are the same. I'll just cancel that. So sine x divided by the cos x, I'll end up with a tan x, which is the same as my right hand side. So we've proved that. And then 2.3.2, 2.3.2, they want us to determine the values between 180 and 360. Between 180 and 360, where the identity is invalid or undefined. So remember, we said for something to be undefined, the denominator must be 0. So if I'm to consider my denominator, which was the cos x into 2 cos x plus 1 being equal to 0, before cancelling out, I'll have something like the cos x being equal to 0, or the 2 cos x plus 1 will be 0. So if the cos x is 0, I'll find the arc cos of 0. The arc cos of 0 will be 90. And then I'll also have 270. But 90 is outside of the range of interest, so I'm not going to consider 90 as my solution. Then I'll come this side, I'll move the one that side, and I'll end up with cos x is equal to -1/2. and then the reference angle of this will give me positive 120. So it will be a positive 120. But 120 is below what I need. So which means my x is going to become a 240. My x is going to become a 240. Then when I consider the other part of the invalid, I'll focus on the overall result, whereby my tan of the angle must be equal to infinity. So that's that. Thank you very much. Enjoy the rest of the day. Welcome to this video, and we shall be talking about trigonometry as our topic of interest. So if we are given a Cartesian plane, and this Cartesian, this is known as the x-axis, that's known as the y-axis, and the point of intersection of the x and the y will be known as the origin. So along the x, to your right, we shall have the positive x-axis, and then to the left of the origin